All right, and then we get to 2.6. For 2.6, the main idea is we're going to be relooking at domain and being a little bit more specific, but some of these instructions are still a little more vague. But let's start here. We're going to start by saying, in most cases, domain is negative infinity, whoops, comma, to infinity. Negative infinity to infinity. So really, that's going to be your answer for a lot of these. But there are some interesting issues, and then we'll just say it like this. We'll say, does getting 0 or negatives cause problems? All right. Now, let's also really quickly look back at the parent functions of my graphs. Now, we haven't looked at what we call rational graphs, but I'm pretty sure we'll look at those later. But we don't need to. But the one thing I do want to point out is so far, all of these graphs had an infinite domain except for one of them, and it's this one right here. And so this is what I meant by does getting 0 or getting negatives cause issues? And what I mean by that is, was getting 0 in the thing that gives the function its name causing issues? So notice that this is the only graph that doesn't go left forever and right forever. It's stopped right here at 0. You can be 0. You just can't get anything. You can't be anything less than 0, because you would then be square rooting a negative, and try it in your calculator, it will say non-real answer. And so this graph does not have an infinite domain because, as I'm saying it, plugging in negatives would cause problems. So it doesn't go left forever anymore. So that's what I mean by, does getting 0 or negatives cause problems? So for square root graphs, yes, it does. And so now let's look at our examples and see what's going on here. So really what we're asking ourselves, if you're catching those two statements, is, can I plug in positives, zeros, and negatives into this thing and be fine? And hopefully we all agree that the answer is yes. So this one's domain is negative infinity to infinity. No issues there. All right, now the question is, this is technically by name a rational function. Rational means fraction, and look at where your variable is, it's on the bottom. And so the question is, for a fraction, is 0 where the variable would be in the denominator? Would zeros or negatives cause issues? And rather, what I mean is, does getting 0 in the denominator cause an issue? And the answer is yes. Anything divided by 0, earlier in the section we called that undefined. So there would be a lapse in our domain. And specifically, the issue is if my denominator was 0. And so I'm going to set it equal to 0 and solve. Well, thankfully that's not too hard. That would be x equals negative 7. Now, to add some extra symbols and catch this real quick, what we're really saying is, I don't want my denominator to be 0, so x cannot be negative 7. All right, so there's, in essence, my domain, but now let's write that in interval notation. I can be anything except negative 7. How do we write that? Well, I can go left forever up until I get to negative 7, but I cannot be negative 7. And then, because it's only split right here, we're going to introduce this thing called a union symbol. This is sometimes referred to as a cup. It's not a capital U. You'll see it as an option on your homework. And then I write another parentheses and write negative 7 to infinity. And this is really weird looking, but hopefully you can see that what this is really saying is, you can be anything to the left of negative 7, you can be anything to the right of negative 7, but you cannot be negative 7 itself. It totally is not allowed to be plugged in, because you would get 0 in the denominator, which is big issue. So your domain is split into two pieces that are right next to each other, but they are two distinct pieces. And we'll study what that graph looks like later. Okay, from there, Does getting 0 in either of these x's or plugging in negatives cause issues? The answer is no. I'll have some stuff to work out and double negatives might occur, but I've got no issue in my domain there. So that's an easy one. Notice again how abstract that statement is, though. I'm just saying theoretically, if I plugged in negatives or 0, do issues come up? And I'm doing a lot of mental effort there to figure that out, but the short answer is no, it doesn't cause issues. All right, up next, we've got another fraction. And so, again, really, because we have a fraction and we have variables in the bottom, I'm concerned about if this could ever be 0. Could this equal 0? And, well, once again, like I warned, factoring is going to show up all the time, and that's what we now have to do. We have to factor this and break it down into its parts. And also, again, I know I'm saying I want to know where this equals 0, but that's because I can't have those values in my domain. It's the same algebra, but just remember that we're technically saying I want to know where this is 0 so that I can say my domain is anywhere I don't get what we're about to solve for. Well, let's solve it. We're looking for factors of 32 that add to 23. Let's see here. There's 132. There's 1 and 132. Those definitely don't add to 23. There's 2 and 66, but those don't add to 23. I think 3 goes in, and we would get 43. Not 43, 44. So once again, those don't add to 22. It looks like I could then plug in 4 and get 33. Once again, those don't add. Could I plug in 5? No. Could I plug in 6? Yes, I could. If I plug in 6, I would get 22, but those don't add to 23. Could I plug in 7? I don't think so. Could I plug in 8? I think so. If I plug in 8, why can't I think about it right now? Oh, and I couldn't think about it because it actually doesn't work. So what about 9? 132 divided by 9, that doesn't work. Goodness. 10's not going to work. 11 might work, and it does. And I got 11 and 12 was the next one that works. And it's the last one. Here's why we write this in order, just to catch this. It's the last one because there's nothing between 11 and 12, so I've now crossed over to the other side of the list if I'm going in order. So sorry that took so long, but that's why we write them out and try them all out individually. We eventually end up at the last possible pair. Well, 11 and 12 will add to make 23, and based on what we learned in factoring, that means I'm ready to jump to my parentheses, and I'm able to tell as I write them out that they both need to be positive to add to make the 23, and they need to both be positive to multiply to the positive 132. And what we're saying is these cannot be 0, and that's actually easy to tell. It means x cannot be negative 11, because plugging in negative 11 would make this whole thing 0, and then it would multiply and make 0. It also can't be negative 12 for the same issue. All right. This is, in essence, your domain, but how do, again, we write that in interval notation? Well, here's how. I can be all as far negative as I want until, careful, in the number line, I would encounter negative 12. Then I can't be negative 12 exactly. And from there, I could then be just to the right of negative 12 until I get to, well, not too far, negative 11, and I have another break. And sorry, I need another union symbol and I'm running out of space. But then I could go from negative 11 to infinity. Let me just erase that. To infinity. And that would be my domain. So sorry that got in the way a little bit when we were writing out those factors. But your domain is split into 3 pieces because, again, in the number line, think about the number line, the negative 12 would be further to the left than the negative 11. So you can be as far negative as you want until you encounter negative 12 and you skip over it, but you get right up to the left of it and right up to the right of it, so to speak. You can then get to negative 11, which wasn't too much farther, so to speak, and then it's split as well, and then we can proceed to infinity. All right, So we again realize that zeros on the bottom is an issue. So where could that algebra on the bottom be zero? And what those values end up being are excluded from my domain because they would cause zero in my denominator. Okay, let's keep going. This one again is the square root. We already talked about that one on the kind of parent function page. Now the issue here is that a square root cannot get negatives on the inside of the root. The issue though is this function's been transformed. Now if you can read the transformation, this is actually pretty easy, but let's talk algebraically how we can determine this. What we're doing here is we're saying I am simply not allowed to get negatives in my square root. Now, another way of phrasing that is, as long as this algebra in my square root is either a positive or is equal to 0, so if I'm greater than 0, aka I'm positive, or if I am 0 exactly, those are fine to be plugged into a square root. Again, here what I'm saying here is I'm saying this is the contents in my root. As long as this contents evaluates to something positive or equals 0 exactly, then that is allowed in a square root. So what's in the square root is what we're saying. All right, well, once again, that's a very quick solve, and x has to be greater than or equal to -7. That's just one quick little subtraction. And so that's my domain right there. I'm done. But if you think about the number line and think about interval notation, what are we saying? We're saying I can go from -7. Oh, but careful. I can be -7. So I get to use a square bracket because this is or equal to. So I can be -7 or I can be greater. Well, greater has an R in it, so we're going to the right. So eventually into the positives to positive infinity. And hopefully you agree with that because again, all this graph did as its parent function was it was here and it went left 7 units. Well, if it moves left 7 units, it can go from -7, its furthest left, still into the positives. But we didn't need to look at the graph to get the domain, we just did some algebra. Now, speaking of just doing some algebra and not worrying about transformations, this one has a little more to it than meets the eye in terms of function transformations. We don't need to talk about that, but just be aware that this isn't simply moving right 30 and I'm done. Just be careful. And so, well, let's not be confusing. Let's just do the same thing because that is the answer. As long as the algebra in the root would be greater than 0, aka positive, or would be 0 exactly, that's fine in a square root. Well, let's solve. You would first just add 30. You would then, whoops, add 30. There's still a 0, but a 3 goes first. You would then divide by 3, and so you would get x is greater than or equal to 10. Now again, that is your domain, but to write it in interval notation, the lowest left I can be, the least value I could be, is 10 exactly, or I could be greater than 10 or to the right of 10, which would go to positive infinity. Now this is what I again meant, hopefully you caught it, that it's not as much of just saying right here, oh, I went right 30, because I didn't go right 30. You actually only went right 10, because there were two threes that could be factored out if you kind of catch that. We don't need to worry about that or be concerned with that. I guess I'm just saying don't automatically look at a -30 and go, ah, I know what to do now. No, no, follow all the algebra on the inside of the root carefully. Okay, this last one is kind of interesting because there's a square root in my denominator. Now, square roots can be 0 or positive, but fractions can't be 0 on the bottom. And so let's see what's going to happen here. Ultimately, I've got my denominator. Here's my denominator. And this denominator cannot be 0, but also this square root has to be 0 or positive. And so if we really strip that away, what we're really saying is, I need this to strictly be positive. Again, I hope you catch that argument, that the square root, maybe we'll just say it like this, could be 0 or positive, but we're saying this can't be 0. So, because of that, taking that all into account, a regular square root says, hey, usually I want the or equal to or greater than, but we're going to throw out the or equal to because it was found in the denominator. After that heavy abstract lifting, we end up with this. X is greater than 5. And so guess what? Greater than 5 is parentheses 5 or greater up to positive infinity. Now, we didn't encounter many where it was single-sided like this and went to negative infinity, but you might on your homeworks later. All right, just be aware of that. Okay, so I know that was a lot of examples to go through, and I know a lot of the examples were the special cases, quote unquote, and that's what we're here to look at in this section, the interesting ones. But what I do hope you realize is that a lot of the time, right, if you're just looking at basic lines or basic parabolas, your domain is super easy to find. If you're even looking at absolute values or cubes, your domain is super easy to find. But once you have algebra on the bottom or you have square roots, that's where your domain either gets split into some sections or you skip over some exact numbers, or it's literally no longer left forever, right forever, and it only is split in kind of one direction and maybe shifted. Okay, where does that take us next? That takes us into, let's see here, a few other questions, and this will probably be where honestly, splitting the video right there is maybe a good place to do it. So we'll go ahead and split the first part of 2.6 right there with just the basics of domain, and then we'll look at this next page.